All right, so this module we talk about the nature of matter and quantization, starts getting pretty weird after a while. Let's watch this. So we'll start out with a couple of crucial experiments historically that led us to our current understanding. One really important experiment, actually, this guy Max Planck was trying to explain this phenomena called blackbody radiation. And scientists had been they just couldn't do it up to that point using their conventional tools. What he did was this guy Max Planck hypothesized that when energy is gained or lost by a system, it's gained or lost not in a continuous manner, but rather chunks of it are gained or lost. And they have a certain size. That's the smallest possible size of energy that can be gained or lost we represent as this, h nu. This is letter H, stands for Planck's constant. I'll show you that in a second. And this is nu. It stands for the frequency. So this is the smallest size chunk of energy that Max Planck said could be gained or lost by a system. So Max Planck was trying to come up with an equation that describes blackbody radiation. Nobody had been able to do that yet. And the only way he was able to do it was by hypothesizing this quantization of energy, by saying that energy is gained or lost in these chunks. That's what we mean by quantization. Blackbody radiation, one form of blackbody radiation is a piece of metal when it's glowing. It's white hot or red hot. That radiation, that part of that radiation given off as visible light, and that's blackbody radiation. So this chunk, h nu, H stands for Planck's constant, and it has to 4 sig figs anyway, the value of 6.626 times 10 to the negative 34th, and its units are joules times seconds. Joules is a unit of energy. So memorize Planck's constant, memorize this little equation here, formula. Nu is the frequency of the radiation that's emitted or absorbed, and its units are inverse seconds or hertz. So the smallest unit being h nu, when a system gains or loses energy, the change in energy of that system is going to be some integral multiple of h nu. N stands for an integer. Actually, let's do it this way. N can be 1, 2, 3, or any integer up to infinity. So, gains or loses energy. One way for that system to gain or lose energy is to emit or absorb what are called photons. I'm sure you've heard of them, photon torpedoes and all that. So the change in energy of the system is, n times h nu, and if it's losing or gaining one photon, the energy of that photon is h nu, Planck's constant times the frequency. It's the energy of one photon. And remember, we also know a relationship from the last module between the frequency and the wavelength. Remember, that guy was this. Let's write it down here. The wavelength times the frequency is equal to the speed of light in a vacuum. So if we know the frequency, we can find the wavelength and vice versa. So here's an example. We want to find the energy in kilojoules of 1.00 moles of photons that have a wavelength of 59.9 nanometers. So what we're going to do, we know that the energy of a photon, these photons are being absorbed or emitted by some system. The energy of a photon is equal to h nu. The change in energy of the system, which is the energy of a photon, is h nu. Okay, and so we're given the wavelength, right? So first thing we're going to do is use this little equation to convert wavelength to frequency. So just rearranging this a little bit, we get frequency is equal to c over lambda. Remember, we memorized c, the speed of light in a vacuum, this number right here. And all I do with these prefixes, remember from our prefixes, nano means times 10 to the minus ninth. I just replace the n with what it means, so 59.9 times 10 to the minus ninth meters. That meter still stays there. Less chance of messing up this way. Anyway, plug these numbers in, and we get the frequency is 5.004 times 10 to the 15th hertz, or inverse seconds. Now that we know the frequency, we can plug into this equation to find the minimum change in energy of the system, which is the energy of one photon, which is Planck's constant times the frequency. So Planck's constant, we're going to memorize that, times the frequency we just got. And this is how much energy one photon has being absorbed or emitted by this system, 3.32 or so times 10 to the minus 18th joules. We're not done yet because we want to know the energy in kilojoules of 1 mole. So what do we do now? I'll just multiply by Avogadro's number. You guys remember Avogadro's number? 6.022 times 10 to the 23rd. If you don't, you should make sure you memorize this. So if there's this much energy in one photon and there are this many photons in a mole, then the units of photons cancel out. We end up with joules over moles, and we get about 1.997 times 10 to the 6th joules per mole. Finally, converting to kilojoules, replace the prefix K, kilo, with what it means, 1,000 or 10 to the third, and we get our answer, 2.00 times 10 to the third kilojoules per mole.